hopefully we'll be wrapping up chapter 5 today. Get through this pretty quickly, hopefully. And then we'll have a quiz test, whatever you want to call it, on Tuesday for chapter 5. But in the meantime, we'll be covering solving recurrence relations by iteration. Suppose you have a sequence that satisfies a certain recurrence relation and initial conditions. It is often helpful to know an explicit formula for the sequence, especially if you need to compute terms with very large subscripts or if you need to examine the general properties of the sequence. Such an explicit formula is called a solution to the recurrence relation. In this section, we'll discuss methods for solving recurrence relations. The method of iteration. The most basic method for finding an explicit formula for a recursively defined sequence is iteration. Iteration works with given a sequence defined by a recurrence relation and initial conditions. You start from the initial conditions and calculate successive terms of the sequence until you see a pattern developing. At that point, you guess an explicit formula. Let the sequence A be the sequence defined recursively as follows. For each integer k greater than or equal to 1, a sub k equals a sub k minus 1 plus 2, and a sub 0 equals 1. Use iteration to guess an explicit formula for the sequence. Well, basically you have the method of substitution where you substitute numbers for k and calculate from there. Now use the initial condition to begin a process of successive substitutions into these equations, not just of numbers, but of numerical expressions. So, you start with a sub 0 equals 1, then a sub 1 equals a sub 0 plus 2, so it's 1 plus 2, and then that substitutes in for a sub 1 on a sub 2 for calculating a sub 2, and so on and so forth. And you can see where a pattern subsequently develops. So you would it appears helpful to use the shorthand k times 2 in place of k 2 plus 2 plus 2 k times. We do so starting again from a0. So you have 1 plus 2, 1 plus 2 times 2, 1 plus 3 times 2, so on and so forth. So you can guess that the explicit formula for a sub n would be 1 plus 2n. So a sequence like the one in which each term is equal to the previous term plus a fixed constant is called an arithmetic sequence. Definition. A sequence A is called an arithmetic sequence if and only if there is a constant d such that a sub k equals a sub k minus 1 plus d. It follows that a sub n equals a sub 0 plus dn for every integer n greater than or equal to 0. As an example, the force of gravity, an object falls in a vacuum about 9.8 meters per second faster each second than it fell the second before. Thus, neglecting air resistance, a skydiver's speed upon leaving an airplane is approximately 9.8 meters per second, 1 second after departure, 19.6 meters per second, 2 seconds after departure, and so forth. If air resistance is neglected, how fast would the skydiver be falling 60 seconds after leaving the airplane? Well, let S sub n be the skydiver speed in meters per second, n seconds after exiting the airplane, assuming there's no air resistance. Then S sub 0 is the initial speed. Since the diver would travel 9.8 meters per second faster each second than the second before, S sub k equals S sub k minus 1 plus 9.8 meters per second. It follows that this is an arithmetic sequence with a fixed constant of 9.8. And thus, it would be S sub n would equal S sub 0 plus 9.8 n. "60 seconds after exiting and neglecting air resistance, the skydiver would travel at a speed of 9.8 times 60 meters per second, or 588 meters per second. Now that's really, really fast. That's almost Mach 2. The speed of sound is approximately 350 meters per second. So it'd be moving at a pretty good clip. Fortunately, there is air resistance and reduces the speed considerably. So, okay. Another example, let R be a fixed non-zero constant, and suppose the sequence A is defined recursively as follows. A sub k equals R, A sub k minus 1 for each integer greater than or equal to 1, and A0 equals A. Use iteration to guess an explicit formula for this sequence. Now, if A is R times A, if for A1, A2 would be R times A, or R squared A, and so on, R cubed times A. So you could guess that A sub n would be R to the n times A, or A times R to the n, for any arbitrary integer n greater than or equal to 0. Definition. A sequence A is called a geometric sequence if and only if there is a constant R such that A sub k equals R sub k times A sub k minus 1 for each integer k greater than or equal to 1. And it follows that A sub n equals A sub 0 times R to the n for each integer n greater than or equal to 0. As was shown in example 567, if a bank pays interest at a rate of 4% per year compounded annually, and A sub n denotes the amount in the account at the end of the year, n, then A sub k equals 1.04 times A sub k minus 1, assuming no deposits or withdrawals during the year. Suppose the initial amount is deposited is 100,000, and assume no additional deposits or withdrawals are made. How much will the account be worth at the end of 21 years? how many years will it in how many years will the account be worth $1 million? Well, A is a geometric sequence with initial value 100,000 and a constant multiplier 1.04. So A sub n equals 100,000 times 1.04 to the n for integers greater than or equal to 0. After 21 years, the amount in the account would be 100,000 times 1.04 times to the 21st power, or $227,876 and some change. That was the same answer that was obtained in example 5, 6, 7, but is computed much more easily, at least if a calculator with a powering key is used. Let t be the number of years needed for the account to grow to $1 million. Then 1 million equals 100,000 times 1.04 to the t power. Dividing both sides by 100,000 gives you 10 equals 1.04 times to the t power. And taking the natural logarithms of both sides results in that equation there. And then take the t out, and t equals natural log 10 over natural log 1.04, which equals about 58.7 years. So it would take that long to get $1 million out of a $100,000 initial deposit. Now, why they threw this in here, I'm not sure, but this is some quantities that are approximately equal to certain powers of 10. Number of seconds in a year, about 10 to the 7th. Number of bytes of memory in a personal computer, it's more than that now. These are older slides, so not 10 to the 9th, but considerably more than that. That's only 1 billion. It's 10 times more than that, so maybe 10 to the 10th. Number of neurons in the human brain, 10 to the 11th. 10 to the 17th, age of the universe in seconds, according to a particular theory. 10 to the 31, number of seconds to process all possible positions of a checkers game if moves are processed at a rate of 1 billion per second. Number of atoms in the universe, 10 to the 81st power. And 10 to the 111th power, the number of seconds to process all possible positions of a chess game if moves are processed at a rate of 1 billion per second. More atoms, more than the number of atoms in the universe. Using formulas to simplify solutions obtained by iteration. Recall that the Tower of Hanoi sequence, M1, M2, M3, etc., satisfies the recurrence relation M sub k equals 2m sub k minus 1, and has the initial condition M1 equals 1. Use iteration to guess the explicit formula for the sequence, and make use of a formula for the sum of a geometric sequence to simplify the answer. By iteration, you have 2 times m plus 1, or m1 plus 1 is 2 times 1 plus 1, or 2 to the first plus 1. So substitute that in, to m sub 3, and you get 2 to the second power plus 2 plus 1. Substitute that into m4, and you get 2 to the third plus 2 to the second plus 2 plus 1, so on and so forth. So these calculations show that each term up to m5 is a sum of successive powers of 2, starting with 2 to the 0th power equals 1, and going up to 2 sub k, or to the k, where k is 1 less than the subscript of the term. The pattern would seem to continue to higher terms because each term is obtained from the preceding one by multiplying by 2 and adding 1. Multiplying by 2 raises the exponent of each component of the sum by 1, and adding 1 adds back the 1 that was lost when the previous one was multiplied by 2. For instance, n equals 6 would be n to the 5th plus n to the 4th plus n to the 3rd, so on. All right. So it would seem that in general, m sub n is 2 to the n minus 1 plus 2 to the n minus 2 plus and so forth until 2 to the second plus 2 plus 1. By the formula for the sum of a geometric sequence, theorem 5.2.2, that would equal to 2 to the n minus 1. Hence the explicit formula seems to be m sub n equals 2 to the n minus 1 for every integer n greater than or equal to 1. Checking the correctness of a formula by mathematical induction. So you can see from some of the previous examples, the process of solving a recurrence relation by iteration can involve complicated calculations. It is all too easy to make a mistake and come up with the wrong formula. That is why it is important to confirm your calculations by checking the correctness of your formula. The most common way to do this is to use mathematical induction. We have obtained a formula for the Tower of Hanoi sequence. Use mathematical induction to show that this formula is correct. Well, what does it mean to show the correctness of a formula for a recursively defined sequence? Given a sequence of numbers that satisfies a certain recurrence relations and an initial condition, the job is to show that each term of the sequence satisfies the proposed explicit formula. In this case, you need to prove the following statement. If m is a sequence defined as it is here, then m sub n equals 2 to the n minus 1 for every integer n greater than or equal to 1. Proof of correctness. Let m be the sequence defined by specifying that m sub 1 equals 1 and m sub k equals 2 times m sub k minus 1 plus 1 for each integer k greater than or equal to 2. Let the property p of n be the equation m sub n equals 2 to the n minus 1. We will use mathematical induction to prove that for every integer n greater than or equal to 1, p of n is true. Next, we show that p of 1 is true. Well, p of 1 is 2 to the 1 minus 1, which is 1. And the definition from the recurrence relation is m sub 1 equals 1, therefore they are equal. And p sub 1 is true. Now show that for every integer k greater than or equal to 1, if p sub k is true, then p sub k plus 1 is also true. Suppose that k is any integer with k greater than or equal to 1. such that m sub k equals 2 to the k minus 1, which is the inductive hypothesis. We must show that m sub k plus 1 equals 2 to the k plus 1 minus 1 is the case. But the left-hand side of the formula p sub k, or p of k plus 1 is m 2 m k plus 1 minus 1 plus 1, which is 2m sub k plus 1. By substitution of the inductive hypothesis, you get 2 to the k plus 1 minus 2 plus 1, or 2 to the k plus 1 minus 1 by basic algebra, which equals the right-hand side of p of k plus 1. Since the basis and inductive steps have been proved, it follows by mathematical induction that the given formula holds for every integer n greater than or equal to 1. Discovering that an explicit formula is correct. Well, let C be a sequence defined as follows. C sub k equals 2c sub k minus 1 plus k for each integer k greater than or equal to 1, and c sub 0 is equal to 1. Suppose your calculation suggests that C satisfies the following explicit formula. C sub n equals 2 to the n plus n for every integer n greater than or equal to 0. Is this formula correct? Well, start to prove the statement by mathematical induction and see what develops. The proposed formula satisfies the basic step of the inductive proof, since on one hand, C sub 0 equals 1 by definition, and on the other hand, 2 to the 0 plus 0 equals 1 plus 0, which is equal to 1. In the inductive step, you suppose that k is any integer with a k greater than or equal to 0, such that C sub k equals 2 to the k plus k, the inductive hypothesis. And then you must show C sub k plus 1 equals 2 to the k plus 1 plus k plus 1. To do this, you start with C sub k plus 1, substitute from the recurrence relation and use the inductive hypothesis. And by basic algebra, you get 2 to the k plus 1 plus 3k plus 1. To finish the verification, therefore, you need to show that 2 to the k plus 1 plus 3k plus 1 equals 2 to the k plus 1 plus k plus 1, which doesn't quite add up. So now the equation is equivalent to k equals 0 or k equals 0. But this is false since k may be any non-negative integer. For instance, when k equals 1 and k plus 1 equals 2, you get C2 equals 2 times 3 plus 2 plus 2 times 3 plus 2 are 8, whereas 2 squared plus 2 equals 6, which is not the case. They are not equal. So the formula does not give the correct value for C2, hence the sequence does not satisfy the proposed formula. And that's it for that slide deck. Now this one gets a little bit weird, and The sequences, mathematical induction and recursion continued with this mouthful. Second order linear homogeneous recurrence relations with constant coefficients. Quite a mouthful. What does that mean? Well, a second order linear homogeneous recurrence relation with constant coefficients is a recurrence relation of the form little a sub k equals big A times little a sub k minus 1 plus b times little a sub k minus 2 for some integer k greater than or equal to some fixed integer, where a and b are fixed real numbers with b equals 0, or not equal to 0. So, which of the following is a second order linear homogeneous recurrence relation with constant coefficients? Well, this one satisfies that because a and b are both integers, and a sub k minus 1 and a sub k minus 2. So this is a second order linear relation. This has the constant coefficients being 1, but it's a third order because it has k minus 3. This one works out as well. This is not a linear homogeneous recurrence because it's d squared. And this one, it works because b is not 0, even though a is. This is not a second order linear, second order relation because it doesn't have the f sub k minus 2 in it. This one does, so that one is a second order linear relation. This one is not because the coefficient is not constant. B is not a constant value. So yes, no, yes, no, yes, no, and yes and no. Distinct roots case. Lema 581. Let a and b be real numbers, a recurrence relation of the form a sub k equals this value, this equation here, for every integer k greater than or equal to 2, is satisfied by the sequence 1, t squared, t cubed, etc. to 2 to the n, t to the n, I mean, where t is a non-zero real number, if and only if t satisfies the equation t squared minus at minus b equals 0. So, given a second order linear homogeneous recurrence relation with constant coefficients, the characteristic equation of the relation is t squared minus at minus b equals 0 if k in the recurrence relation is greater than or equal to 2. Consider the recurrence relation that satisfies that the kth term of a sequence equals the sum of the k minus 1 term plus twice the k minus 2 term. That is, a sub k equals a sub k minus 1 times 2 times a sub k minus 2 for each integer greater than or equal to 2. Find all sequences that satisfy the relation and have the form 1 t, t squared, t cubed, etc. to tn, where t is non-zero. By lemma 581, the relation is satisfied by a sequence given here, if and only if t satisfies the characteristic equation t squared minus t minus 2 equals 0. Since that equals t minus 2 times t plus 1, the only possible values of t are 2 and minus 1. It follows that the sequences 1, 2, 2 squared, 2 cubed, etc., 2 to the n, and 1, minus 1, minus 1 squared, minus 1 cubed, etc., are both solutions for the relation, and there are no other solutions of this form. So the sequences are both solutions. Note that the sequence can be written more simply as 1 times 1, 2, 2 squared, 2 cubed times to 2 to the n, and yeah, it's the same as up here. It's minus 1 to the n power. Lemma 582. If R and S are sequences that satisfy the same second order linear homogeneous recurrence relation with constant coefficients, and if C and D are any numbers, then the sequence A, defined by the formula A sub n equals C times R sub n plus D times S sub n for every integer n greater than or equal to 0, also satisfies the same recurrence relation. Consider the recurrence relation that specifies that the kth term of the sequence equals the sum of the k minus 1 term plus twice the k minus 2 term, which we looked at earlier. Find a sequence that satisfies the recurrence relation and that also satisfies the initial conditions a sub 0 equals 1 and a sub 1 equals 8. Well, consider the sequences from the previous example. Both satisfy the relation, and although neither satisfies the given initial conditions. However, by lemma 582, any sequence A that satisfies the explicit formula A sub n equals C times 2 to the n plus D times minus 1 to the n, where C and D are real numbers, are numbers, also satisfies the relation. So you can find C and D so that the sequence A satisfies the initial conditions specified in this example by substituting n equals 0 and n equals 1 into the equation and solving for C and D. When you simplify, you obtain the system 1 equals C plus D and 8 equals 2C minus D, which can be solved in various ways. For instance, you can add the two equations. You get 9 equals 3C and C equals 3, and then substitute. You know how to solve a system of two equations. That's algebra 2, I think, something like that. But you get a sub n equals 3 times 2 to the n minus 2 times minus 1 to the n for each integer n greater than or equal to 0. And that satisfies both the recurrence relation and the given initial conditions. So the theorem 583, the distinct roots theorem, suppose the sequence A, it satisfies the recurrence relation given here for some real numbers a and b with b not equal to 0, and every integer k greater than or equal to 2. If the characteristic equation t squared minus at minus b equals 0 has two distinct roots r and s, then the sequence A is given by the explicit formula here, where C and D are the numbers whose values are determined by the values A sub 0 and A sub 1. The Fibonacci sequence satisfies the recurrence relation f sub k equals f sub k minus 1 plus f sub k minus 2, with the initial conditions f sub 1 and f sub 0 equal 1. Find an explicit formula for this sequence. Well, the Fibonacci sequence satisfies the first part of the hypothesis of the distinct roots theorem, since the Fibonacci sequence is a second-order linear homogeneous recurrence relation with constant coefficients. A equals 1 and B equals 1. To check that it satisfies the second part of the hypothesis, examine the characteristic equation t squared minus t minus 1 equals 0. By the quadratic equation, it has two roots, and they are distinct. 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2. Thus, it follows from the distinct roots theorem that the Fibonacci sequence is given by the explicit formula C times that mess there plus D times that other mess there to the n for each integer n greater than or equal to 0, where C and D are the numbers whose values are determined by the fact that f0 and f1 are equal to 1. To find C and D, write out this here for f0 equals C plus D, and f1 1 equals C times 1 plus square root of 5 all over 2 times, or plus D times 1 minus square root of 5 all over 2. Thus, the problem is to find C and D such that C plus D equals 1 and this equals 1. This may look complicated, but it is in fact just a simple system of two equations with two unknowns. Solving this equation, this system, we get C equals 1 plus square root of 5 over 2 times the square root of 5, and D equals minus 1 minus 1 minus square root of 5 all over square root of 2 times the square root of 5. Substituting these values for C and D into the formula, and then simplifying, you get this seemingly complex formula here. Remarkably, even though the formula for f sub n involves the square root of 5, all of the values of the Fibonacci sequence are in fact integers. So, the single root case. Let a and b be real numbers and suppose that the characteristic equation t squared minus at minus b equals 0 has a single root r. Then the sequences 1, r to the first, r to the second, r to the third, etc. to r to the n, and 0, r, 2r squared, 3r squared cubed, etc. to n r to times n, n times r to the n both satisfy the recurrence relation here for each integer k greater than or equal to 2. Single root theorem. Suppose a sub k, the sequence A satisfies this recurrence relation for some real numbers a and b, with b not equal to 0 for every integer k greater than or equal to 2. If the characteristic equation t squared minus at minus b equals 0 has a single real root, then the sequence A is given by the explicit formula a sub n equals c times r to the n plus d times n times r to the n, where c and d are the real numbers whose values are determined by the values of a sub 0 and any other known value of the sequence. So suppose a sequence B satisfies the recurrence relation here for every integer k sub k greater than or equal to 2, with initial conditions b sub 1, there b sub 0 equals 1 and b sub 1 equals 3. Find an explicit formula for b for the sequence B. This sequence satisfies part of the hypothesis of the single root theorem because it satisfies a second order linear homogeneous recurrence relation with constant coefficients. The single root condition is also met because the characteristic equation t squared minus 4t plus 4 equals 0 has the single unique root r equals 2. So it follows from the single root theorem that the sequence B is given by the explicit formula c times 2 to the n plus d times n times 2 to the n for each integer n greater than or equal to 0, where c and d are real numbers whose values are determined by the fact that b sub 0 equals 1 and b sub 1 equals 3. To find c and d, you find that c equals 1 and 3 equals 2c plus 2d. So substitution, c equals 1 into the second equation, you get d equals 1/2. Now substitute c equals 1 and d equals 1/2 into formula 5, 8, 12 to conclude that b sub n equals 2 to the n plus 1/2 n times 2 to the n, which in turn equals 2 to the n times the quantity 1 plus n over 2. 1 plus n over 2, yeah. And that is it for that slide deck. Wrap up chapter 5 with section 9. General recursive definitions and structural induction. So sequences of numbers are not the only objects that can be defined recursively. In this section, we discuss recursive definitions for sets and functions. We also introduce structural induction, which is a version of mathematical induction that is used to prove the properties of recursively defined sets. Recursively defined sets. To define a set of objects recursively, you identify a few core objects as belonging to the set and give rules showing how to build new set elements from the old. More formally, a recursive definition for a set consists of the following three components. Base, a statement that certain objects belong to the set. Number two, the recursion, a collection of rules, not just necessarily one, but a collection of rules indicating how to form new set objects from those already known to be in the set. And then there's the third, the restriction, a statement that no objects belong to the set other than those coming from the base and the recursion. The set of Boolean expressions was introduced in section 2.4 as legal expressions involving letters from the English alphabet such as P, Q, and R, and the symbols here, including the parentheses, to make precise which expressions are legal. The set of Boolean expressions over a general alphabet is defined recursively. Each symbol of the alphabet is a Boolean expression. Recursion. If P and Q are Boolean expressions, then the following are also Boolean expressions. A and Q, P or Q, not P, and P in parentheses. Restriction. There are no Boolean expressions over the alphabet other than those obtained from the base and the recursion. Derive the fact that the following is a Boolean expression over the English alphabet A through Z. P and Q, the inverse, or not R and P. Well, by 1, P, Q, and R are Boolean expressions. By 1, 2A and 2C, P and Q and not R are Boolean expressions. By 2D and 2A, P and Q in parentheses are, and not R and P are Boolean expressions. And then these two are Boolean expressions as well, just building up, adding the not in front of that expression and putting the parentheses around that one. And then finally, you have the full expression with the two expressions with an OR by 2B. Certain configurations of parentheses in algebraic expressions are legal, whereas others are not. Here is a recursive definition to generate the set C of legal parentheses structures. Base, open and close, is in C. Recursion. Rule number 1, if E is in C, then so is E in parentheses. If E and F are in C, so is EF. Restriction. No parentheses structures are in P other than those obtained from the base and the recursion. So you can show that this configuration is a parentheses structure in C. Parentheses are in C. Parentheses within parentheses is in C. And then parentheses times parentheses is also in C. Because E by 2B. Recursion is used to give a formal definition for the set of all strings over a finite set. Recursive definition for the set of all strings over a finite set. Kind of a wordy definition, but let A be any finite set. Call the elements of A characters and define the set S of all strings over A as follows. Base, lambda is a string in S where lambda denotes the null string and the string with no characters. Recursion. New strings are formed according to these rules. 2A, if U is any string in S and C is any character in A, then UC is a string in S, where UC is called the concatenation of U and C and is obtained by appending C on the right of U. If U is any string in S, then both the concatenation of lambda and U, denoted by lambda U, and the concatenation of U and lambda, denoted by U lambda, are defined to equal U, symbolically, this here. If U and V are any strings in S, and if C is any character in A, then the concatenation of U and VC is defined to equal the concatenation of U, V, and C. Symbolically, the associative property holds true, basically. Restriction. Nothing is a string in S other than objects obtained from the base and the recursion. The base for the recursive definition of strings only indicates that one character, namely lambda, is a string. The next theorem states that each individual character in the underlying set is a string. If A is a finite set and S is the set of all strings over A, then every character in A is a string in S. Suppose A is a finite set. S is the set of all strings over A, and A and B are in A. Because of the way of the definition of a string is stated, it cannot be deduced immediately that B, open parentheses, A, close parentheses, is a string in S. To prove that this is true, first show that BA and BA concatenated with A are strings in S, and use the fact that BAA and BAA are equal. Well, theorem 591, A and B are strings in S because both A and B are in A. By 2A, rule 2A, BA is a string in S because B is in S and A is an element of big A. BA is a string in S because BA is an element of S and A is an element of S. BAA equals BAA because A and B are strings in S and A is an element of big A. By 3 and 4, BAA is a string in S because it equals to BAA, which is a string in S. Proving properties about recursively defined sets. When a set has been defined recursively, a version of mathematical induction called structural induction can be used to prove that every object in the set satisfies a given property. So, structural induction for a recursively defined set. Let S be a set that has been defined recursively, and let P of X be a property that objects in S may or may not satisfy. To prove that every object in S satisfies P of X, perform the following two steps. The basis step, show that P of A is true for each object A in the base for S. show that for each x in S, the inductive step, show that for each x in S, if P of x is true, and if y is obtained from x by applying a rule from the recursion, then P of y is true. To perform this step, suppose that x is an arbitrarily chosen element of S, for which P of x is true. This is the inductive hypothesis. Then show that if y is obtained from x by applying a rule from the recursion for x, then P of y is true. Conclusion. Because no other objects other than those obtained from the base and the recursion are contained in S, step 1 and 2 prove that P of x is true for every object x in S. So let S be the set of all integers defined recursively as follows. Base condition 4 is in S. The recursion, given any integer n in S, n plus 3 is in S as well. Restriction, no integers are in S other than those derived from the base and the recursion. Use structural induction to prove that for every integer n in S, n mod 3 equals 1. Well, given any integer n in S, let property P of n be the sentence n mod 3 equals 1. Show that P of n is true for each integer n in the base for S. P of 4 is true because 4 mod 3 equals 1, since 4 equals 3 times 1 plus 1. Should now show that for each integer n in S, if P of n is true, and if m is obtained from n by applying a rule from the recursion for S, then P of m is true. Suppose n is any integer in S such that P of n is true. Then n mod 3 equals 1. This is the inductive hypothesis. The recursion for S consists only of one rule, and when the rule is applied to n, the result is n plus 3. To complete the inductive step, we must show that P of n plus 3 is true. By the inductive hypothesis, n equals 3k plus 1 for some integer k. It follows that n plus 3 mod 3 equals 3k plus 1 plus 3, or mod 3, or 3k plus 4 mod 3, which equals 3k plus 1 plus 1 mod 3, which equals 1 by basic algebra. Which means that P of n plus 3 is true. Conclusion. Because there are no integers in S other than those obtained from the base and the recursion for S, every integer n in S satisfies the equation n mod 3 equals 1. N plus 3 mod 3 equals 3k plus 1 plus 3 equal mod 3. A recursive definition can also be given for the length of a string. Given the set of all strings S over a finite set A, the length L of a string in S is defined as follows. Length of lambda equals 0. 2. For every string U in S and for every character A in A, the length of UA is one more than the length of U, symbolically this here. Following theorem states that the length of a concatenation of two strings is the sum of the lengths of the strings. So, additive property of string length. If S is the set of all strings over a finite set A, then for all strings U and V in S, LUV equals LU plus LV. The next theorem extends the operation to pairs of strings. The concatenation of two strings is a string. If S is the set of all strings over a finite set A, and U and V are any strings in S, then UV is a string in S. And then the theorem that generalizes associativity of concatenation of any three strings. The associative property applies if S is a set of all strings over a finite set A, and U, V, and W are any strings in S, then U, VW equals UVW. Now we get into recursive functions. A function is said to be defined recursively or to be a recursive function if its rule of definition refers to itself. Because of this self-reference, it is sometimes difficult to tell whether a given recursive function is well defined. Recursive functions are of great importance in the theory of computation in computer science. The following function, M, positive integers to integers, as defined by John McCarthy, a pioneer in the theory of computation, is as follows. M of n equals n minus 10 if n is greater than 100. If n is less than or equal to 100, m of n equals m of n plus 11. For all positive integers n, find m of 99. Well, by repeated use of the definition of m, you get 91 through your various substitutions. The remarkable thing about this function is that it takes the value 91 for all positive integers less than or equal to 101. That's in an exercise at the end of the section. For n greater than 101, m of n is well defined because it equals n minus 10. So it is a well-defined recursive function. In the 1920s, German logician and mathematician Wilhelm Ackermann first defined a version of the function that now bears his name. This function is important because it uses values that are computable, but cannot be evaluated using only 4 next loops. The function is defined on the set of all pairs of non-negative integers as follows. A of 0 and n equals n plus 1 for all non-negative integers n. A of m and 0 equals a of m minus 1 and 1 for all positive integers m. And m of n, a of m and n equals a of m minus 1 and a of m and n minus 1 for all positive integers m and n. So find a of 1 and 2. Now, by substitution and expansion and all that sort of stuff from the definitions, you get 4. The special properties of the Ackermann function are a consequence of its phenomenal growth rate. While the values of a of 0 and 0 and a of 1 and 1 equals 3 and a of 2 and 2 is equal to 7, not especially impressive, but a of 4 and 4 is approximately equal to 2 to the 2 to the 2 to the 65,536 power. And the values of a and n and n continue to increase with extraordinary rapidity after that. Consider the following attempt to define a recursive function g from positive integers to integers for each integer n greater than or equal to 1. G of n equals 1 if n is 1. G of n equals 1 plus n over g of n over 2 if n is even. And g, it equals g of 3n minus 1 if n is odd and n is greater than 1. Is g well defined? Well, suppose g is a function. Then by definition of g, g of 1 equals 1. G of 2 equals 2. G of 3 equals 4 by substituting things out. And then g of 4, substituting things out, equals 3. But what about g of 5? G of 5 would be g of 14 equal to g of 14, which is equal to 1 plus g of 7, which is equal to 1 of g of 20, which is equal to 1 plus g of 10, which equals 1 plus 1 plus 1 plus g of 5, which is equal to 3 plus g of 5. Subtracting g of 5 from both sides gives you 0 equals 3, which is false. And so the supposition that g is a function leads logically to a false statement. And it follows that g is not a function. And that will wrap it up for chapter 5. So, chapter 5 is all wrapped up. We're going to have a test on it on Tuesday. The homework for chapter 5, I don't know what the deadline is for it in the computer at this point, but I will adjust it to make it midnight on Tuesday. Oh, is it set for Wednesday next week? Oh, okay. I'll just leave it as it is then. Yeah. Have a good weekend. See you next week.